Can you start the audio?
Excuse me?
No, everything is fine.
Okay. So now let's recall that at the previous lecture we discussed, mostly without proofs, some basic facts from the elementary spectral theory in Banach algebras. And at the end of the lecture, we stated the following result due to Gelfand, which asserts the following. If A is a unit to Banach algebra, then first of all, if we take any point in the spectrum of an arbitrary element little a, then we have the following inequality. So the absolute value of lambda is less than or equal to the norm of A. Second, the spectrum of A is compact. It's a compact subset of the complex plane. And finally, what is this is probably the most important part of this theorem. If A is non-zero, then the spectrum is non-empty. So these are the basic properties of the spectrum of a Banach algebra element. And as a corollary of this result implies the so-called Gelfand-Mazur theorem, which classifies Banach division algebras. The classification is very simple, and in fact, it looks exactly as in the finite dimensional case. So if A is a Banach division algebra, which means that it's a unital Banach algebra, a non-zero unital Banach algebra, such that every non-zero element is invertible, then A is actually a field of complex numbers. By the way, in the finite dimensional case, this is a simple exercise in linear algebra to prove this result. This theorem states the same for arbitrary Banach algebras over the complex numbers. So let's recall once again that by default we work only over the complex numbers. And the proof is just a line. We take an arbitrary element of A of our algebra, and since the spectrum is non-empty, can always find a number lambda which is in the spectrum. So by the definition of the spectrum, this means that A minus lambda is not invertible. But on the other hand, by assumption, all non-zero elements are invertible. So we conclude that this element is zero, or equivalently, A is just lambda 1. So we see that A is spanned by the identity element. So it is isomorphic to the complex numbers. By the way, there is also a version of this. Excuse me?
Я вот просто потом разбирался вот по поводу скетча вот пруфа третьей теоремы Гельфанда. Я просто в конце не понял, вы говорили про то, что линейный функционал разделяет точки. Вот, я вот сейчас... А можете, пожалуйста, повторить? Просто не очень понятно было.
Почему линейный функционал разделяет точки? Well,
в смысле любой линейный функционал или что?
No, continuous. Once again, a little short idea of proving part 3. So basically, the idea is to take any linear functional f and to consider the following function. If we assume that the spectrum is empty, then this function is defined everywhere, because A minus lambda is always invertible. The spectrum is empty. So this function is a function of the complex plane to itself. And it can be shown, it's a little auxiliary lemma, that this function is holomorphic. On the other hand, it's a simple estimate shows that this function vanishes at infinity. Well, a continuous function which vanishes at infinity is bounded in particular. And there is a classical Liouville theorem which states that a bounded holomorphic function from the complex plane to itself is constant. So as a result, this function is a constant which vanishes at infinity. In other words, this is identically zero. And now we recall, this is about your question, we recall that this is true for every linear functional, for every continuous linear functional on our algebra. But it follows from the Hahn-Banach theorem that continuous linear functionals on any normed space separate the points. So since this is zero for every f, we conclude that this element A minus lambda inverse is zero. But this is impossible because this is an invertible element. It can be 0 only if the algebra A is 0. So that's the idea. That's the idea. So of course, I skipped some technical points, in particular the proof of the fact that this functional is holomorphic. But the idea is this. So we combine Hahn-Banach theorem and Liouville's theorem on bounded entire functions. Okay, so a few comments about the Gelfand-Mazur theorem. This result has also a version over the real numbers, which states that if you have a Banach division algebra over the real numbers, then it is isomorphic either to the real numbers, or to the complex numbers, or to the quaternions. And in this form, this theorem extends the classical Frobenius theorem, which states the same for finite dimensional division algebras over the real numbers. Well, by the way, why do I say extends? Its simple exercise is to show that every finite dimensional algebra can be made into a Banach algebra. This is very easy. Just consider the multiplication operators which act on this algebra from this algebra to itself, and consider the operator norm. So every finite dimensional Banach algebra, every finite dimensional algebra is a Banach algebra, and so the real version of the Gelfand-Mazur theorem extends the Frobenius theorem. And by the way, there is this result has a remarkable history. First, it was announced without proof by Mazur in 1938. And his paper was actually about the real case, which is much harder than the complex case. But for some strange reason, Mazur submitted his paper to a French journal, Comprendu, which is known to publish only brief communications, just a few pages. And shortly, Mazur received a reply from an editor of the journal, which said that, well, your paper is very interesting and it contains original results, but it's too long for our journal, so I have to reduce it. And the only reasonable way to reduce the paper was just to throw away the proofs. So as a result, Mazur's paper contained only statements, no proofs. And the first published proof of this result was given by Gelfand in 1941, but it was only over the complex numbers. So this result, which we've just discussed, was proved by Gelfand over the complex numbers. And the first published proof of the real version of this theorem appeared only in the 1960s in a book by Charles Rickard on Banach algebras. Okay, the next.
Excuse me, but what is the real version of this theorem? What is the statement?
It states that if A is a Banach division algebra over the real numbers, then it is isomorphic either to the real numbers or to the complex numbers or to the quaternions. Exactly as in the Frobenius theorem. But now for Banach division algebras, possibly, which are not assumed to be finite dimensional. So they turn out to be finite dimensional automatically, but this is not assumed from the very beginning. Okay, so our next little goal is to discuss, to recall the notion of spectral radius in Banach algebras. Also, this discussion will be rather sketchy because, again, this material is traditionally included in standard functional analysis courses. So suppose that A is a unital Banach algebra. Again, we assume from the very beginning that it is non-zero. We take an element little a of our algebra, and we define the spectral radius of this element by the following formula. So geometrically, this means that the spectral radius is the radius of the smallest disk of the smallest closed disk centered at 0 and containing the spectrum. So this is the spectrum. And this is the disk of radius ROA. So if we call Gelfand's theorem, it states that for every lambda in the spectrum, the absolute value of lambda is less than or equal to the norm. And this implies that after we take the supremum, this implies that the spectral radius of A is less than or equal to the norm of A. Sometimes, in some concrete examples, these two numbers are actually the same. For example, if you take the algebra of bounded functions on an arbitrary set X, then the spectral radius of A is actually equal to the norm of A. Well, indeed, let's recall that the spectrum of A is just the closure of A of X, the closure of the range of A. So the supremum of this set, more exactly, the supremum of the absolute values of numbers in the set is nothing but the supremum norm. And so we have the equality. And the same argument shows that this is true for many other Banach function algebras, in particular for the algebra of continuous bounded functions on a topological space. Another simple example is the algebra, if you take the algebra of linear operators on a finite dimensional Hilbert space. And let's take an operator little a, which is diagonalizable with respect to a suitable orthonormal basis. So it can be written as on the following diagonal matrix. So in this case, the spectrum, well, its space is finite dimensional, so the spectrum consists of all eigenvalues of the operators, which are on the diagonal. So we see that the spectral radius is just the maximum in the set of all eigenvalues. But on the other hand, it's easy to show that this is exactly the norm of it. So again, in this case, we see that the spectral radius equals the norm. And here is a counterexample which shows that sometimes the inequality is strict. Let's take the algebra of operators on the two-dimensional space and consider the operator, which is represented by the following upper triangular matrix. So in this case, the spectrum is 0, because for the upper triangular matrices, the spectrum is concentrated on the diagonal. So the spectrum is 0, and as a result, the spectral radius is also 0. But of course, the norm is positive, because the operator is non-zero. So in this case, the spectral radius is strictly smaller than the norm. And in fact, this example can be generalized as follows. If you take any algebra A, any unital algebra A, and an nilpotent element little a, then the spectrum of this element is 0. So the spectral radius is also 0. So as a result, for any nilpotent element in a Banach algebra, for any non-zero nilpotent element of Banach algebra, the spectral radius is strictly smaller than the norm. In the general case, the spectral radius is given by the following remarkable formula. The respective result is often called the Berling-Gelfand theorem, but actually this result is due to Gelfand. Berling proved this formula only in a very special case of his own algebra, of a very concrete Banach algebra, studied by himself, the so-called Berling algebra, which is, well, in some sense, this is a weighted version of the group L1 algebra of the integers. We discussed the group algebras of discrete groups at the previous lecture. So if you take the group of integers and add a suitable weight to the definition of the norm, then what you get is the Berling algebra. And this result was proved by Berling for his own algebra. And the proof was used some specific features of this algebra. And the general result, for which works for an arbitrary unital Banach algebra, is due to Gelfand. So the spectral radius is given by the following nice formula. So for every n, we take the nth power of A, we calculate the norm of this element, and take the nth root of this number. And then we take the limit. The limit will be equal to the spectral radius. Or equivalently, we can take the infimum and the result will be the same. I'll not give you all ingredients of the proof. Again, this is a standard. This is a part of the standard course of functional analysis. But the idea is the following. If we want to show that the spectral radius is less than or equal to this infimum, this is very easy. This follows from the fact that if lambda is in the spectrum, then lambda to the power n is in the spectrum of a to the power n, and so the absolute value of lambda to the power n is less than or equal to the norm of a to the power n. And then we take the nth root of both sides and take the infimum over n. And we get this inequality. The opposite inequality is much more involved. The proof of the opposite inequality is much more involved. Again, it uses some ideas of complex analysis. So again, we start with an arbitrary continuous linear functional f on a, and consider the following function of a complex variable. It is defined everywhere on the open disk of radius 1 over r away, and it can be shown that this function is holomorphic in this disk. So we can decompose it into the Taylor series, and then it turns out that the Taylor coefficients of this series can be calculated explicitly. They are exactly f applied to a to the power n. This follows from the fact that if lambda is small enough, then this element can be decomposed as this usual geometric progression, lambda to the power n times a to the power n. And after we apply f, we get the power series in lambda with such coefficients. And then by using the convergence of this series in this disk, and by making some simple elementary algebraic manipulations, we deduce that actually the spectral radius of A is greater than or equal to this infimum, and actually greater than or equal to the upper limit of this sequence, which automatically implies, since R of A is greater than or equal to the upper limit, but is less than or equal to the infimum, this automatically implies the existence of the limit. So this is the main idea of the proof. As a corollary, we see that the spectral radius of A is 0, even only if this limit is 0. And if we write this explicitly, so this number is less than epsilon if n is big enough, this means that we have the following asymptotics of a to the power n. So the norms of a to the power n converge to 0 faster than any geometric progression. So this characterizes elements with 0 spectral radius. And actually, there is a special name for such elements. Such elements are called quasi-nilpotent. So by definition, an element is quasi-nilpotent if its spectral radius is 0, or equivalently, if its spectrum is 0. Well, the name quasi-nilpotent is, well, it's quite natural, because if A is nilpotent, then this sequence is eventually 0, and this condition holds. This condition is satisfied. But it can happen that an element is quasi-nilpotent, but is not nilpotent. And here is probably the most classical example of such an element. Let's consider the so-called Volterra integral operator. This operator is determined by a bounded measurable functional k on the square AB cross AB, and it acts on the space L2 over the interval AB by the following formula. So the integral is taken with this, from A to X, and we integrate this product. And it can be shown, actually this is a useful exercise, to show that this operator is quasi-nilpotent. Actually, the norms of the powers of this operator can be estimated explicitly, and it turns out that they behave something like 1 over n factorial. So 1 over n factorial satisfies this condition. It converges to 0 faster than any geometric progression. The second nice corollary of the Berlin-Gelfand formula is as follows. Suppose that A is a unital Banach algebra, and suppose that B is a closed subalgebra of A, which contains the identity. So they have a common identity. So let's recall that in this situation, if we take an arbitrary element B of the smaller algebra, then the spectrum of B calculated with respect to the bigger algebra is smaller than the spectrum of B calculated with respect to the smaller algebra. But it turns out the spectral radius is the same. The spectral radius of B calculated with respect to the smaller algebra is equal to the spectral radius calculated with respect to A. And this is immediate from the Berlin-Gelfand formula because, well, this number is the same if we change our algebra to a smaller Banach subalgebra. Everything depends on the norm, on the norms of the powers of A. Actually, there is also a stronger result. It turns out that if we compare the spectra of this element calculated with respect to these two algebras, A and B, then it turns out that the spectrum of B calculated with respect to the smaller algebra can be obtained from the spectrum with respect to the bigger algebra by filling in some holes in the spectrum. So more exactly, this means that the spectrum of B calculated with respect to A is the union of the spectrum of this element with respect to with respect to the smaller algebra B is the union of the spectrum of this element with respect to A and some connected components of the complement of the spectrum. But this is a little bit harder. This will be an exercise in our first exercise sheet. Okay. That's all I wanted to tell you about the spectral radius. And let's now concentrate on commutative Banach algebras. The main ingredients of the theory of commutative Banach algebras are the maximal spectrum and the Gelfand transform. Okay, so let's start with some purely algebraic preliminaries. Suppose that A is a commutative unital algebra. So at this point, A is not assumed to be equipped with a norm. So we consider it purely algebraic case, just the commutative unital algebra over the complex numbers. Actually, we can consider arbitrary commutative unital rings as well. And suppose we have a proper ideal I of A. And we say that I is a maximal ideal if it is not contained in any strictly bigger proper ideal J. If there is no such proper ideal J such that I is strictly smaller than J. In other words, the maximal ideal is the maximal element in the partially ordered set of all proper ideals of A. Of course, maximal doesn't mean that it is the biggest ideal. In the general case, there can be many different maximal ideals, and this is quite typical. Sometimes it's useful to interpret this property in slightly different terms, and this is a useful exercise. It can be shown that an ideal I is maximal, even only if the quotient of A modulo I is a field. This is a useful algebraic exercise for you. And now we can introduce the maximal spectrum of A. So by definition, the maximal spectrum of A is the collection of all maximal ideals of A. Here's a simple example. Let's look at the polynomial algebra in one variable t. Then it's a simple exercise to show that there is a one-to-one correspondence between the maximal spectrum of this algebra and the complex plane. More exactly, if P is a point on the complex plane, then the corresponding maximal ideal of the polynomial algebra consists of all polynomials which vanish at little p. This is a simple exercise in pure algebra. By the way, the same result also holds for the polynomial algebra in several variables. But in this case, this is not trivial. And actually, this is a weak form of Hilbert's Cauchy-Tellin-Satz. How about the existence of maximal ideals? Well, they do exist. And more exactly, we have the following result, which states that every proper ideal of A is contained in a maximal ideal. The proof is the standard application of Zorn's lemma. So we start with the proper ideal I of A, and we denote by M the collection of all proper ideals of A, proper ideals J of A, which contain I. So this set is obviously non-empty because it contains I itself. It is a partially ordered set for the inclusion relation. And I claim that this set satisfies the condition of Zorn's lemma. Well, why is it so? Well, we have to prove that every chain, every totally ordered subset of M has an upper bound. So we take a chain C in M, and we denote by K the union. We denote by K the union of all ideals belonging to the chain. It's easy to observe that this union is actually an ideal. It is an additive subgroup, stable under multiplication by elements of A. So it is an ideal of A, and it contains I for obvious reasons. But if we want, so of course we want K to be an element of M, and we have to show that K is a proper ideal. And this is the point where we use the assumption that our algebra is unital. Just a moment, I will have 10 minutes left of our Zoom session, after which we will have to reconnect with the same link. So I want to. Okay, well, I'll try to not to miss this. Okay, so why is it proper? Well, A is a unital algebra. So an ideal is proper if and only if it doesn't contain the identity of A. So we see that for every element J in our chain, the identity of A is not in J. And this implies that the identity of A is not in K. And this implies that K is a proper ideal. So K is a proper ideal. So it is an element of M, and it is an upper bound for our chain C. So we see that every chain has an upper bound, and by Zorn's lemma, our set M has a maximal element. And this completes the proof. Okay, let's now introduce another set, which is closely related to the maximal spectrum. We define a character space of A, and we denote it by A hat, to be the collection of all non-zero characters of A. So let's recall that a character is just an algebra homomorphism from A to the complex numbers. And let's also recall that every non-zero character is automatically unital. It takes the identity of A to the identity. It's clear, well, how is this set related to the maximal spectrum? It's more or less clear that for every character chi of A, its kernel is a maximal ideal. Well, indeed, it is an ideal because chi is a homomorphism, and it is maximal because it is codimension 1 subspace. Chi is a linear functional, so its kernel has codimension 1. So it is maximal not only in the set of all proper ideals, but also in the set of all vector subspaces.
Извините, пожалуйста, вы можете, пожалуйста, напомнить, что выше там было? Я что-то забыл определение максимального спектра.
the maximal spectrum, well, this is the definition.
Yeah.
So the maximal spectrum is just
Спасибо.
the set of all maximal ideals.
Хорошо, спасибо.
A set of all maximal ideals. And an ideal is maximal if it is maximal by inclusion. So there is no bigger proper ideal in our algebra. So the kernel of every character is a maximal ideal because it has codimension 1. It is an ideal because a character is a homomorphism, and a homomorphism, the kernel of any ring homomorphism is an ideal, and it is a subspace of codimension 1, so it is maximal. So we see that we have a map. We have a map from the character space to the maximal spectrum, which takes every character to its kernel. And I claim, it's a simple proposition, that this map is always injective. Well, indeed, why is it so? We take two characters, suppose that chi1 and chi2 are two characters with the same kernel. It's a simple fact of linear algebra that two linear functionals with the same kernel can differ only by a constant multiple. So there is a constant lambda such that this relation holds. And now we substitute the identity here, and we call that both chi1 and chi2 are unital. So we have this chain of equalities, which implies that lambda is actually 1, lambda is 1, and so chi1 equals chi2. So we conclude that our map from a head to the maximal spectrum is injective. In many concrete examples, this map is actually a bijection. For example, if we take the polynomial algebra in one variable, then this map is a bijection. This readily follows from our earlier exercise about the maximal spectrum of the polynomial algebra. So this concrete maximal ideal is just the kernel of the evaluation map at P. And in fact, can be deduced from Hilbert's Nullstellen Satz that if A is a finitely generated commutative algebra over the complex numbers, then this map is also a bijection. On the other hand, here is a counterexample. Suppose that A is an arbitrary field properly containing the complex numbers. For example, the field of rational functions of one variable. Then it's a simple exercise to show that the character space is empty. We have no characters at all. The character space is empty. But the maximal spectrum is non-empty. The zero ideal is maximal because A is a field, so if we quotient out the zero ideal, we get the same algebra A. So it's a field, and as a result, the zero ideal is maximal. So in this case, of course, our map is not bijection. Okay, so our next goal will be to show that if A is a commutative unital Banach algebra, then this map is always a bijection. And this will be deduced from the following useful lemma, which states that if A is a commutative unital Banach algebra, then every maximal ideal of A is closed. Every maximal ideal of A is closed in A. Okay, why is it so? We take a maximal ideal I in A, and we observe, it's a little exercise, which is actually very easy, that the closure of an ideal is also an ideal. The closure of an ideal is also an ideal. This easily follows from the continuity of the multiplication. So the closure of I is an ideal. And let's assume that I is not closed. So the closure of I is strictly bigger than I. But I was a maximal ideal. And by the maximality of I, we conclude that the closure of I is not a proper ideal. So in other words, the closure of I is equal to A. Or equivalently, in other words, this means that I is dense. I is dense in A. what does that mean? A set is dense if the intersection of the set with an arbitrary non-empty open set is non-empty. But we already know that the set of all invertibles in A is open. This was discussed at the previous lecture. So as a result, the intersection of I with the set of invertibles is non-empty. In other words, I contains invertible elements. But if an ideal if an ideal contains invertibles, then it is equal to A. And this is a contradiction because I was assumed to be maximal ideal. In particular, I was a proper ideal. So this contradiction implies that actually I equals I, the closure of I, so I is closed. I is closed.
Сейчас коммутативность используется где?
Коммутативность особенно на самом деле не используется. At this point, we didn't essentially use the commutativity assumption of A. In fact, we could take with non-commutative algebras, but later the commutativity assumption will be more essential. At this point, we could consider a left ideal, for example, only left maximal left ideals or maximal right ideals. In general, they are not the same, but in any case, any maximal ideal of a Banach algebra, of a not necessarily commutative Banach algebra, is closed, and also every maximal right ideal is also closed. Okay, so as a corollary of this lemma, we see that a commutative unital Banach algebra doesn't have dense proper ideals. Well, indeed, every proper ideal is contained in maximal ideal, but maximal ideal is closed. So a proper ideal cannot be dense. Okay, at this point, probably it's time to make a short break for technical reasons. So, as our free Zoom meeting is. Okay, let's continue. So now by using this lemma, we can prove that if A is a commutative unital Banach algebra, then our map from the character space of A to the maximal spectrum, which takes every character chi to its kernel, is a bijection. So we know that in the general case, it is injective, but is not necessarily surjective. So for Banach algebras, this is a bijection. So before we prove this theorem, let's make a little observation. If A is an arbitrary Banach algebra, not necessarily commutative, and if I is a closed two-sided ideal of A, then the quotient of A modulo I is also a Banach algebra with respect to the quotient norm. Well, the quotient norm is given by this formula. Well, indeed, it's a standard fact that this quotient is a Banach space. So the quotient of a Banach space modulo a closed vector subspace is also a Banach space for the quotient norm. On the other hand, it's an algebra because I is a two-sided ideal. So, and it's a very simple exercise to show that this quotient norm is submultiplicative. So we deduce that this quotient is also a Banach algebra.
Я не понял по поводу, а почему вот это отображение будет сюрреактивным?
Вам еще не доказали.
Все, я подумал, что это
Нет, пока this was just a preliminary observation. So now let's give the proof. So we start with the maximal ideal I, and we consider the quotient of A modulo I. So it's a field because I is a maximal ideal. And it follows from this previous our preliminary observation that this is a Banach field. And now we apply the Gelfand-Mazur theorem, which implies that this quotient is isomorphic to the complex numbers. And now it's very easy to construct a character such that I is the kernel of this character. Well, indeed, we consider the quotient map of A onto the quotient of A modulo I, and compose this quotient with the isomorphism between A modulo I and the complex numbers. So as a result, we get a character whose kernel is exactly I. So as a result, every maximal ideal is a kernel of a character. And that's it. So of course here
we don't need the commutativity for
no,
this.
here we need the commutativity. Here we need the commutativity
Uh,
because otherwise, well, if we consider closed left ideals, the quotient of A module a closed left over a maximal left ideal is not an algebra at all.
No, but if we consider only two-sided ideals, two-sided maximal ideals, the fact is
Two-sided maximal ideals, in this case, the quotient will be simple. This will be an algebra which doesn't have a proper two-sided ideals, but a simple algebra is not necessarily a division algebra, and as a result, it is not necessarily the complex numbers. So we cannot.
So the factor by maximal two-sided ideal isn't always a field?
No. Well, take the algebra of square matrices, of square n by n matrices. The zero ideal is the maximal two-sided ideal because the algebra is simple. So the zero ideal is maximal, but the algebra is not a field, it's not commutative. So if we try to apply the same to two-sided ideals in a non-commutative Banach algebra, then we'll fail. And there are numerous examples of numerous examples of simple Banach algebras which don't have non-trivial two-sided ideals at all.
So in the state of in the statement of Gelfand-Mazur theorem, we also require the Banach algebra to be commutative, not just division algebra.
It is a division algebra. No. In the statement, it is not necessarily commutative. But my point is that a simple algebra, an algebra which doesn't have proper two-sided ideals, is not necessarily division algebra. If it is commutative, then this is true. A commutative unital algebra without any ideals is a field. But a non-commutative algebra without two-sided ideals is not necessarily a division algebra.
Okay.
Like for example, the basic example is the metric. The basic example to keep in mind is the matrix algebra. It is simple. It doesn't have proper ideals. The only proper ideal is zero, but it is not a division algebra. So here the commutativity is essential.
Yeah, thanks.
Okay, so let's continue. So as a corollary of this theorem, we get the following useful invertibility criterion for an element of a commutative unital Banach algebra. So if A is a commutative unital Banach algebra, then an element little a is invertible if only for every character of A, chi of A is non-zero. To the left-to-right implication is clear because chi is a unital algebra homomorphism, so it takes invertibles to invertibles. And so chi of A is non-zero. And to prove the right to left implication, we assume that little a is not invertible. If it is not invertible, then the principal ideal generated by this element is proper. And since it is proper, it is contained in a maximal ideal. There exists a maximal ideal I, such that this principal ideal is contained in I. But we already know that I is the kernel of a character. And as a result, we deduce that this character vanishes at little a. Now, this completes the proof. Okay, so from now on, it will be convenient to identify the maximal spectrum of A with a character space. This is useful because sometimes it is more convenient to interpret elements of the set as characters, and in other situations, it will be more convenient to look at them as maximal ideals. So everything depends on the situation. So we will freely identify them by using this canonical bijunction. Okay, so far the set, the maximal spectrum, is just a set without any extra structure. And our next goal will be to make it into a topological space. So we want to define a nice topology on this space. Before we can do it, let's make a short digression into functional analysis, and let's recall some basic facts on the weak star topology, on the dual of a normed space. So suppose that E is a normed space. We take an arbitrary element little v in our space, and we define a semi-norm on the dual on E star by the following simple formula. So this is just the absolute value of f of v. And by definition, the weak star topology on the dual of E is the locally convex topology generated by the family of all such semi-norms. Well, explicitly, if you forgot what that means, what is the locally convex topology generated by a family of semi-norms, well, this is not essential, because we can write explicitly some typical open sets for this topology. So more exactly, if we take an arbitrary continuous linear functional f on E, then the standard subbase of neighborhoods of this element for the weak star topology consists of all sets of the following form: U, V, epsilon of F. So they are indexed by elements V in our space and positive numbers epsilon. And this basic set, or more exactly sub-basic set, U, V, epsilon of F, consists of all continuous functionals G for which the following inequality holds. So this is the standard subbase of neighborhoods of F. If we take their finite intersections, then we get a base of neighborhoods of F. So this is the definition of the weak star topology. And let's recall some basic properties of this topology. First of all, it's easy to show that this topology is always Hausdorff. Second, if we interpret E star, the dual space, as a subspace in the space of all complex valued functions on E, then it's easy to see that the weak star topology is nothing but the restriction to E star of the product topology on C to the power E. This is more or less immediate from the definition of this standard subbase of neighborhoods in E star. So actually the same formulas determine the product topology on the space of all complex valued functions on E. As a corollary, we see that a sequence Fn in E star converges to F for the weak star topology, if and only if it converges pointwise. This is true because this is true. Excuse me?
Сейчас, ограничение, это в смысле вы имеете в виду, что мы пересекаем все вот,
just
в смысле это индуцированной топологии, да?
Yeah,
Okay.
the induced topology. I mean that the topology on E star induced from C to the power E is just the weak star topology. Now the next property looks as follows. Let's introduce the following notation. So for every element V in E, we denote by epsilon V the evaluation map from E star to the complex numbers, which takes every functional F to F of V. Then I claim that the weak star topology is actually the weakest topology on E that makes all all evaluation functionals continuous. This is also very easy, and this is immediate from the definition of this, from the construction of this topology. This observation implies the following, part 4. If X is an arbitrary topological space, and if we have a map from X, a map phi from X to E star, then this map is continuous for the weak star topology. If and only if for every element V in E, the composition of phi and the evaluation map is continuous from X. This easily follows from part 3. The next fact is related to the canonical embedding of E into the bidual. So let's recall that every normed space E can be isometrically embedded into the bidual into E double star by the following formula. So we take every V and we consider the evaluation function of epsilon V. So I claim that the range of this map, the image of this map, is nothing but the set of those continuous functionals on a star, which are weak star continuous, weakly star continuous. This is not immediate, but this is more or less standard fact. The next fact we need is related to linear operators. If you have two normed spaces E and F, and the linear operator between the duals, a linear operator T, from F star to E star, then this operator is continuous for the weak star topologies, even only if it comes from an operator between E and F. Or more exactly, if there exists a bounded linear operator S from E to F, such that S is the dual, such that T is the dual of S. And finally, the final result we need, final result about the weak star topology we need, is the classical Banach-Low-Glue theorem, which states that the closed unit ball in the dual space is weakly star compact. That is, it is compact in the weak star topology. By the way, let's recall that it is never compact in the norm topology, unless E is finite dimensional. If E is infinite dimensional, then this ball is not compact for the norm topology, but it is always compact in the weak star topology. Okay, so let's now come back to Banach algebras. So we take a commutative unital Banach algebra A. We look at the maximal spectrum of A. So we follow our convention that this set is identified with the character space of A. And we recall that every character is continuous. This was proved at the previous lecture, that a character of a commutative, sorry, not necessarily commutative actually, any character of a unital Banach algebra is continuous. And its norm is less than or equal to 1. So A hat, the character space, is a subset in A star. So we define the Gelfand topology on the maximal spectrum, or equivalent on the character space, to be the restriction of the weak star topology on A star. That is the induced topology on A hat. So as a result, we see that the maximal spectrum becomes a topological space. A nice property of the space is that the space is always compact and Hausdorff. Well, indeed, why is it so? We have already observed that A star, the dual space, is Hausdorff for the weak star topology. And since A hat is a subset, it is also Hausdorff. Now, why is it compact? Well, since the norm of a character is less than or equal to 1, we see that A hat is actually contained in the closed unit ball, in the closed unit ball way. And the closed unit ball is compact for the weak star topology. So now to prove that A hat is compact, we have to show that A hat is closed in the unit ball. Again, closed for the weak star topology. And to prove that it is closed, we do the following. We consider the following two maps from A star to the complex numbers. We take two elements A and B in our algebra. So the first map takes every functional f to the following number, f of AB minus f of A, f of B. And the second map is just the evaluation at the identity. And now we observe that both maps are continuous for the weak star topology. Well, indeed, we know that the evaluation maps are continuous. So f of AB is continuous, f of A is continuous, f of B is continuous. So the product of two continuous functions is continuous. The difference of two continuous functions is continuous. And as a result, the whole map is continuous. And the second one is just the evaluation map, so it is also continuous. So both maps are continuous. And now we observe that A hat, the character space, consists exactly of those functionals f for which the following two identities hold, for every A and B. So as a result, by the continuity of these maps, we conclude that A hat is closed in the closed unit ball. And since the closed unit ball is compact, we deduce that A hat is also compact. Okay, so this completes the proof. So the maximal spectrum is always compact and Hausdorff. Now we are ready to introduce the Gelfand transform of our algebra. So we start with an arbitrary element little a in our algebra. And we define its Gelfand transform, A hat, to be the following function on the maximal spectrum, or equivalently on the character space of A, which is given by the following simple formula. So it takes every character, a little x of A, to chi of A, to x of A, sorry, to x of A. So this looks trivial, actually. This is trivial, but this is very useful. So what can we say about this function A hat? I claim that this function is continuous. Well, indeed, why is it continuous? Let's observe that A hat is nothing but the restriction to the character space of the element I of A, where I of A is the result of the canonical embedding of A into the bidual, just by the definition of the canonical embedding. But we have already recalled that I of A, this element I of A, is weakly star continuous. This is a weakly star continuous functional on A star. And so A hat is continuous because it is the restriction of a continuous map. And that's it. So this can be done for every element little a of our algebra. And as a result, we get a map from A to the algebra of continuous functions on the maximal spectrum. So this map takes every element little a to the function A hat, to the Gelfand transform of this element. And this map is called the Gelfand transform of the algebra. The Gelfand transform of the algebra. The following result describes some basic properties of the Gelfand transform. First of all, I claim that the Gelfand transform, gamma, is a unital algebra homomorphism from A to the algebra of continuous functions. Second, the norm of this homomorphism is equal to 1, except for the trivial case where the algebra A is 0. Next, I claim that if we take an element in our algebra, little a, then the supremum norm of its Gelfand transform is nothing but the spectral radius of it. The spectrum of A, the spectrum of our element A can also be conveniently described in terms of the Gelfand transform, and I claim that the spectrum of A is nothing but the range of the Gelfand transform. And finally, the kernel of gamma, the kernel of the Gelfand transform is equal to the intersection of full maximal ideals of A. And this is also equal to the collection to the set of all quasi-nilpotent elements in our algebra. So these are the basic properties of the Gelfand transform. Okay, so part one is a simple exercise. The fact that gamma is a unital homomorphism is immediate from the definition of gamma. And now it will be convenient to prove part 4, to prove that the spectrum of A is equal to the range of the Gelfand transform of A. To prove this equality, let's recall that the range of A hat is nothing but the spectrum of A hat as an element of the algebra of continuous functions. So this was discussed at the previous lecture. The spectrum of a continuous function is of continuous function f is the range of f. So we have this equality. So now property 4 is about the equality between two spectra, the spectrum of A and the spectrum of A hat. And this was also discussed at the previous lecture that a unital homomorphism between unital algebras preserves the spectrum, if and only if it takes non-invertibles to non-invertibles. So we see that now we see that property 4, equality 4, is reduced to proving that gamma takes non-invertibles to non-invertibles. Well, why is it so? To prove that it has this property, we take a non-invertible element in our algebra, and we recall the invertibility criterion, which was discussed 15 minutes ago. Since this element is not invertible, then we can always find a character chi which vanishes at A. But this means exactly that A hat, the function A hat, vanishes at the point chi. So A hat is not invertible in the algebra of continuous functions. And so we see that gamma takes non-invertibles to non-invertibles. And this implies property 4. This implies this equality. Okay, now property 3, the equality between the norm of a hat and the spectral radius, is immediate from part 4. So we simply look at these two sets, so they are the same. And so after we take the maximum of absolute values of elements in this set, what we get is exactly this equality. So RA is the maximum of absolute values in this set, and the norm is the maximum in this set. So they are the same. So this implies property 3. To prove property 2, so property 2 states that the norm of gamma is 1. Why is it so? If we take an arbitrary element in our algebra, the supremum norm, we already know that the supremum norm of a hat is equal to the spectral radius of A, but we also know that the spectral radius of A is less than or equal to the norm of A. So the norm of a hat, as a result, the norm of a hat is less than or equal to the norm of A. And this means that the norm of gamma is at most 1. The norm of gamma is at most 1. But on the other hand, gamma is unital, takes the identity to the identity, and so its norm is actually equal to 1, except for the trivial case where the algebra is 0. Finally, let's look at the kernel of a gamma. So by the definition of gamma, its kernel is just the intersection of the kernels of all characters. This follows immediately from the definition of the Gelfand transform. But we already know that the kernels of characters are exactly the maximal ideals of it. So it is equal to the intersection of all maximal ideals. And finally, to see that this set is equal to the set of all quasi-nilpotents, we look once again at property 3. So this is 0, even only if this is 0, even only if the spectral radius is 0, which means that A is quasi-nilpotent. So the kernel is equal to the kernel of gamma is equal to the set of all quasi-nilpotent elements. And this completes the proof of our theorem. By the way, the set which appears in part 5 of our theorem, namely the intersection of all maximal ideals, has a special name. It is called the Jacobson radical. In fact, the definition of the Jacobson radical makes sense for every commutative unital algebra, not necessarily Banach algebra, and more generally for any commutative unital ring. So by definition, the Jacobson radical is the intersection of all maximal ideals. And we say that A is Jacobson semi-simple if the Jacobson radical is trivial. By the way, so we have just proved that the Jacobson radical of commutative unital Banach algebra is equal to the set of all quasi-nilpotents. And for those of you who are a little bit familiar with commutative algebra, it will be instructive to compare this situation with prime ideals. You probably know that if we consider the collection of all prime ideals in A, then the intersection of all prime ideals also has a special name. This is the so-called nil radical of A, and it consists of all nilpotent elements. So in the general case, the set of all prime ideals, the prime spectrum, is bigger than the maximal spectrum. So the intersection of all prime ideals is smaller than the intersection of all maximal ideals. And this is for Banach algebras is trivial because, well, every nilpotent element is quasi-nilpotent. Okay. A simple but useful corollary of our theorem is that the range, the image of the Gelfand transform, is a spectrally invariant subalgebra in the algebra of continuous functions on the maximal spectrum. In other words, let's recall that this means that an element in the subalgebra is invertible in the subalgebra if and only if it is invertible in the bigger algebra of all continuous functions. And why is it so? If we assume that gamma way is invertible in the algebra of all continuous functions, we recall that gamma, where is it? We recall that gamma takes non-invertibles to non-invertibles. Gamma takes non-invertibles to non-invertibles. So, in other words, if gamma way is invertible, then A also has to be invertible. A is also invertible. But now applying gamma again, we see that gamma way is actually invertible in the smaller algebra, in the image of gamma. And this means exactly that the image of gamma is spectrally invariant in the algebra of all continuous functions. Okay. Well, okay, I see that now we have less than 10 minutes left, and probably there is well, probably it's better to stop here today. So at the next lecture, we consider some concrete examples of the Gelfand transform. In particular, we discuss the Gelfand transform of the algebra of continuous functions on the compact Hausdorff topological space. And we will see that the Gelfand transform of C of x, or the algebra of continuous functions on the compact space X, is the maximal spectrum is canonically identified with X. And under this identification, the Gelfand transform becomes just the identity map of C of x to itself. And this result actually can be extended to numerous subalgebras of C of x, to many Banach function algebras. So if a Banach algebra if commutative Banach algebra A consists of functions on a compact topological space X, then in many cases, not always, but under some natural assumptions, we will see that the spectrum is identified with X, and the Gelfand transform is identified just with the tautological inclusion of A into C of x, which is quite useful. And we also discuss the functorial, some useful functorial interpretation of the Gelfand transform. Next, we briefly discuss what happens if our algebra is not unital. This is unavoidable because, I have already said at the previous lecture that there are numerous concrete examples of non-unital Banach algebras, and we must consider a non-unital case as well. So in the non-unital case, this theory of commutative Banach algebras has to be slightly modified, but anyway, we will see that most results about commutative Banach algebras, and in particular about the Gelfand transform, survive in the non-unital case as well. And then we we'll begin to discuss C-star algebras. I will discuss some of their basic properties, and we will prove the first fundamental result on C-star algebras, which states that if A is a commutative unital C-star algebra, then the Gelfand transform of A is actually an isometric isomorphism. So as a corollary, every commutative unital C-star algebra is isomorphic to the algebra of continuous functions on the compact topological space. Okay, so that's all for today.
Спасибо. До свидания.
До свидания.